Hey guys, you may notice I'm still at home, and that is true. Um, Even though I did move into college, basically, sometimes I'll still be going home for like the weekends and stuff, and this just happens to be one of those days. So, I promise you'll probably see the college background soon, just like not today. Yeah, a lot of things have changed. I'm also on a Mac right now, which I may or may not have talked about, and it's kind of proving to be very annoying in a lot of ways, but yeah. So I've got a new setup, although it's pretty much the same. I still have like the same like compilation commands and stuff like that. Um, Except I've not found a way to know. I don't think there's a way to run Notepad++ natively. And one of the ways to fix that is to like use a VM or something, but that's kind of dumb. So I don't really want to try that. So I'm looking for some new editor. I've heard there's stuff like Genie and stuff like that. I'm just using this thing called TextMate because it's like really simple, and I do like simplicity. But I would probably find something different, at least something that has tabs, because this is kind of annoying to not. Um, what else was I gonna say? Oh yeah, I also forgot the recording stuff I use. So hopefully this built-in laptop mic is good enough. And I don't have the drawing tablet, which is kind of annoying. But yeah, I'll figure something out, I guess. Anyway, yeah, it's also like late because I spent a lot of time setting up OBS. So right now I'll update the sub count so that we can get started. Actually, what I want to do first is do want to figure out, do I have something to draw with? I'm pretty sure I don't have MS Paint anymore either. So let's see. Alright, let me look this up. I'm doing my setup live. I'll have some timestamps and stuff. Preview? Is that a thing? Preview. How do they call it that? Okay, well it has to open an image. Sketch. Is the thing. Okay. Come on. Yeah, okay. I'll go for that. Sure. That seems cool. Um. Okay. Just make sure this is fine. Yeah, it's got a thing on Google. It's probably trustworthy. Alright, yeah, downloading a drawing app live. We'll see how this goes. Okay, thank you for not doing that. Now, are you open? Or are you just not open? What are you trying to... Oh, it wants to open an image. Ah, I hate that. Okay. It's like everything has to open an image. I can't just have just a thing that... Oh my god. Alright, why is everything so annoying? Do you Mac people like know something better that I can use? Because I don't like this. So I just want to like, I want to like Paint. I can just open it and then it doesn't have to modify an image. It can just make a thing for itself. I don't remember what that is. Go to desktop, and then where are the screenshots I have? Okay, that one's fine. This is a very good picture of the Facebook Hacker Cup. Alright, so the way this works is now I can draw over it, but I can't. That's loud. Okay. But I can't actually. Alright, well, this is annoying. So I guess to do this, can I expand this in some way? No, that's not gonna work. It's not gonna work. What do I have to do? Image size. Okay, let's do like 500. Let's do 1,000 actually. Can I zoom? Okay, I will take that. Well, I can do this. Sure. That kind of works. Okay, anyway. Now that we're done with this segment, and I don't know why you're in full screen. Oh, because I told you to be in full screen. Now that we're done with this segment, we can get to the actual contest now. Yeah. Be happy for timestamps, because you don't have to watch all that. Alright, so you have a grid with 2 rows and n columns. Fully cover the grid using n dominoes. Yeah, place them vertical or horizontally. So you see one row, help Bob and figure out what the other row should be. Well, that's awful. Okay, so if it's valid, then okay. Okay. I'm not used to this. I guess I can alt tab still. So if it's valid, then like if you have something like L and R, and this row isn't filled in, then there's no way that you can have anything on either of these, because there's no way to have, God, there's no way to have like, the only way you would have something in this row is if you had an up here, and therefore you would need it down. So if you have an L here, then there's nothing here. And if you have an R here, then there's nothing here. And because you have L's and R's together, because the dominoes are like 1 by 2, that means that when you have an L and R here, then there's not going to be any piece of domino here or any piece of domino here, meaning both of these cells are going to be empty. So what you can do is you can place a horizontal domino right below the L and the R to complement it, or to like make it work for the second row. So basically, if you have a horizontal domino, you can put another one right there. So if you see any L and R, you can print an L in the same position and an R in the same position, and it would work. In fact, the samples do hint to that. And that's because these horizontal spaces are going to be empty. If you have an up, then it means the domino is like this. So no matter what, you have to print down because, or you have to print D because that's like, it's the bottom half of the domino. The domino's there. So basically, if you encounter an L and R, you print the same character, and if you encounter a U, then you have to print a D, because that's the only other character that works. So let's do that. U C is equal to D. Oh, I don't even need to. Yeah. So we read in the string. If it's L and R, we leave it unchanged. Otherwise, we do change it. It should work. Do I have the test case number? Still did Facebook Hacker Cup. What? What? Reading test case. Oh. There is a length. Which makes no sense, but okay. DLR, LR, DLR. Yeah, sure. I wonder if there's a way to rebind hotkeys. Because I also don't like the fact that, like, they changed the control key to be, like, not in the corner. Which means that it's really hard to do, like, fluid motions of chaining hotkeys because my, like, finger on the, like, the command key is just awkward. What did I mess up? What did I print? Wait, let's just look at that. Oh. Whoops. Wait, what? Oh, D is the, wait, what? Oh, it can be either row. Okay, so if you encounter a D, then the other, it has to be a U otherwise. Okay, I didn't realize you can give both rows. That's stupid. Doesn't really add anything to the problem. But sure. Anyway, yeah, so if it's U or D, you switch the character so that you get the other half of the domino. Can spam that pretty quickly. That's nice. All right, you get A and B. You write an array of non-negative integers with the mex equal to, oh, God, this type of problem. The mex is equal to A, the XOR is equal to B. What is the shortest possible length? Okay, so I love looking up formulas. Okay, so we know because the mex is A, by definition, like say we have A, so by definition we have the numbers 0, 1, 2, dot, 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 up to A minus 1. Then we don't have A, and then we can have any of these numbers repeated and we can have any other number. But we have to have these numbers. So the question is this enough? That's a text. Let me check that. Well, the question is that enough? I'll respond to that later. Is that enough? Or at least after I finish this problem. So, well, we can find the XOR of all of these. You can do it manually, although that doesn't really work. So what you would need to do, how do I change the color? Okay. See straw. All right, that is a wide array of colors. I like that. So the question is that enough? And so what we can do is we can find the XOR of all these numbers because we have to have them in the array anyway. We might as well assume we have them. Now, if the XOR is exactly B, then we're golden. If it's not B, then we need to figure out what it actually is. If it happens to be A XOR B, then the easiest way to correct it would be to append A to the array. But of course that doesn't work because we can't have A in the array. So what we need to do instead is, we can't do one number, so the best we can do is two numbers. And we can, we just need to add two numbers that aren't A, but XOR to A. And there are a lot of ways to do this. You can pick any X and add A XOR X and X to the array. It should be fairly intuitive that there's always going to be such a pair, because you can pick any X and eventually you'll find one that works. Like if you use like 2 to the x equals like 2 to the 50th, for example. Because these numbers are pretty small, 2 to the 50th is never going to be touched. It's never going to be a. So it's going to be fine if we do that. So it's 2, and otherwise the number is not a, which means we can directly add that number to the array, and we can make our XOR be in one number. So essentially, the length of the array initially is a, because we need all those elements. Samples are okay. The initial thing we need is a, and then we think about like the XOR as well. Where's my text editor? I'm so used to Notepad++. Okay, so the hardest part is finding the XOR of all numbers up to a minus 1. We can do it with a bit of casework. And the reasoning behind this casework is that I want this bigger actually. Image size 200%. Okay. And I can't zoom out any farther. Awesome, love this. Okay, actually it's sort of normal. Wait, what? Oh. That doesn't do anything. Sigh. Okay. I gotta find a better image editor. So, geez, like, I have fruits. Everything is a fruit. Why is that the case? So the point is these things will repeat. So I'll just write out some of the XORs. Oh, okay. I guess it's smaller now. Sure. So I'll write out some of the XORs. So we have 0, 1, 2, and it's lagging, which is cool. It's lagging like crazy, actually. All right. So the point is the XOR of every group of 4 numbers is equal to 0. You can verify that yourself. Because 0, XOR 1, XOR 2, XOR 3 is 0. Then all of these numbers are 4 XOR 0, 1, 2, and 3. Like this is 0 XOR 4. 5 is 4 XOR 1. 6 is 4 XOR 2, and so on. And so because we have 4 numbers, this will cancel itself out. And we already know these numbers cancel each other out. And it'll just like keep going on this way. So essentially every 4 numbers, we end up with 0. So the question is now, what is a minus 1 mod 4? Where is it in this cycle? So I'll use 4, 5, 6, and 7 as an example. I really want my old computer back. Where's 4, 5, 6, and 7? So initially, this XOR is 4. This XOR is 4 XOR 5, which is going to be 1. Then this is going to be 7. And this is going to be 0. So how does this work? Well, if it's this, then this just returns n, because n is going to be 4 here. If this is 1, then it's 1. If it's this, then it's n plus 1, because this is 1 XOR n, and n is even, so the 1 is going to add 1. And the last part is 0. So this is sort of the casework. Basically, depending on a minus 1 mod 4, we're going to get some different stuff. So let's just do that. If a minus 1, minus a. How does this work? So if a mod 4 is equal to 0, I need to refer to my own casework. Ans is equal to a. And now it's XOR is equal to a. X equal to 1. Alright, so if x is equal to b, do nothing. because we're already good. Yeah. This is the similar casework. If it's equal to ax or b, then we need to add a, but we can't, so we add 2. Because we need 2 different numbers, otherwise we only need 1 different number. Three, 2, 3, 3, 4. Okay. Why? Three, 2, 3, 3. So it's 2. Why am I adding 2 every time? I want you to close. Get out of here. Now I'm really confused about what is happening here. Why would you get 3? Why would you add 2 every time? What am I messing up here? Wait. This can't be a thing, could it? It is a thing. Okay, precedence matters. Got it. Okay. Well, that fixes it then. So the problem is it was doing x equals a, and then that x or b, which I guess had problems. What the hell? What is happening? So yeah, I guess let's not do that again. And I'm gonna trust it, because again, recently I have not been caring about penalty. I've made that pretty clear. So if I get wrong answer, it doesn't matter. Okay, I'm gonna check that text. God damn it. Now I have to open this app again. Okay. I will be right back. Do this problem in the meantime. Oh my god. My god, what is with that problem? That just seems annoying. We're talking about carrying. Yeah, this is about textbooks, which I should get fairly soon. Okay. Alright, Alice has just learned addition. However, she hasn't learned the concept of carrying fully. Carries the column 2 columns to the left. We have to find the number of pairs of positive integers. Awesome! 2039 plus something. Now we have to figure out a process and then analyze it, and then we have to understand it, and then we do problem based on it. Okay, so is there like any nice way to do this? I doubt it. We go like digit by digit or something. Or is that digit DP? How many solves does this have actually? I'll look at that. Not that many. So it seems like a pain, is what I'll say. I kind of want to look at D. I kind of don't want to do this problem. And positive integers in base 10 with some S. Holy crap. What is with these problems? So I want to give as much weight to the as much weight to something. As much weight to the later digits, I guess. Has to be positive integers, which is also a pain. So here we're talking about weird carrying. Here we're talking about minimizing carrying. Is that the idea? Is there any problem that isn't annoying? Could we get that instead of... Alright, let's try this one. This one seems more sane. Q operations of two types. So update the element. Calculate how many non-decreasing subarrays exist. Actually going to rage quit this contest. Jesus Christ, what are these problems? Why are they asking this? Like, what are they gaining out of asking this stuff? This is just annoying segment tree stuff. Like, that, I mean, maybe there's, I don't know. That's what it appears to be, because that's very, like, very known problem. Or at least it's just that type of, like, standard, like, maintain some stuff going on. Why are they doing this? What are they doing? Why would they do this? This is so annoying. What next? I'm just gonna read all the problems right now. In an empty grid with n rows and m columns, some of the cells are marked, no marked cells are adjacent to the edge of the grid. unmarked cell, either the number 1 or 4. Where's the no? Is there a no? There is a no. So corners don't matter. I have to do 5. 5 must matter somehow. Okay, so some cell is adjacent to an odd number of unmarked cells, and they are screwed. That is a thing. So some cell can only be adjacent to an even number of unmarked cells, because that's what the 1 and 4 is for. Otherwise, there is no way to do it so that you can do that. So now what? I guess where does the hard part come in? I don't know why they have N or M at least 1. That seems pointless, but whatever. So if something is adjacent to 2 unmarked cells, then we have a constraint that those 2 must be opposite each other. Something is adjacent to 4 unmarked cells. Like a checkerboard, for example. Then what must happen is that certain ones are complements of each other. Only one of these samples has that. Okay, so the question is, how do we handle the ones that are adjacent to 4 unmarked cells? Well, something has to happen. You could frame it as 2-set, kind of. Actually, it's not 2-set, it's worse. Yeah, it's much worse. Okay, so that's not 2-set, so never mind. Basically, like, we need 2 1s and 2 4s here. That is the requirement. So we need to fill in the grid such that there are 2, 2 something. Like 2 of each, right. Also of note, if something has 4 empty things next to it, then it's sort of free. Or it like obviously it has nothing adjacent to it, which makes sense. Um, so then what? You can try and reduce it to like an instance of 2 coloring or something. We have certain things that are opposite each other. Is there ever a need for where's my red? Let's say something like everything is literally fruit. So let's say this has 4 empty cells next to it. I'm not even trying at this point. I'm sort of thinking that it's possible to do something like where these are the same and these are opposite. And then we sort of force the construction to be like that. And so that makes it automatically, so if something's in this cell, then it's perfect. If something's like here, for example, then it should be fine either way. And actually, sort of a question. It's like basically this is what we do with fours. We say these are going to be the same and these are going to be opposite. And if that's true, then the rest of the problem is easy. If not, then I don't know what to do. But I'm interested in that. Because if that's true, then we can make a clause that says this must be the same color as this. This must, if this is 1, the other one is 1. This must be the same as this as well. And these must be different. And that is all stuff we can represent as a 2 coloring problem, unlike a graph. Guessing it should always be possible, but I'm not really sure. And so the other part is like, okay. Is there ever a case where it matters otherwise? Like, I'm not really sure when that would be the case. Because otherwise, we're gonna do something like we do, maybe like this. Then we get an extra 4 here, an extra 1. Nope. What? I'm doing the command. Okay. Yeah, we got something like that. And then maybe if we have something like here, and maybe here and something, then we have ones here and we have ones here. And so we sort of keep up this pattern of like, if we have something here, then it'll work because these will be opposite each other. My concern is that it might not like always work. But the question is, when would that not work? I just want to try it. Let's just see. Whoa, wait. Okay. Actually, I have no idea how to prove this. Yeah, no idea. Absolutely no idea. But it sort of feels like it should work just because, like it's sort of better to do that. Because if we do it the other way, if we have something like this, 1, 4, 4, 1, for example, then if we have another cell here, and these are all blocked off, then this one's screwed. But if we do it the other way, then that cell will not be screwed. Is the thing. So I'm not exactly sure what to do with that. But I'm guessing there's some symmetry argument hidden within that makes, not symmetry, I don't know what it is actually. But I kind of just want to try it. That'd be funny if it works. If it doesn't work, I'll code E and then maybe like try and think about these. I kind of just don't want to do these problems. Like this one just seems like a pain. It might not be a pain, but it seems like it is a pain. And I don't like that. So 505. Okay. Now, first, if anything is adjacent to 1 or 3 unmarked cells, then we're screwed. I do like that they have it so it's not on the edge. That is a convenience thing. It is strictly for convenience, I'm assuming, and that is very nice of them. So I do appreciate that. dr4 is equal to 0, 0, 1, 1. Yeah. We're just simulating the directions. If mat ij is equal to x, count is equal to 0. For LD equals 0, d is less than 4, d plus plus. Ni is equal to I plus drd, and j. We're just going in that direction. If mat ni and r is equal to dot plus plus count. So yeah. If count mod 2 is equal to 1, pos is equal to 0. It's a constraint on the input, not a checking thing. So if not pos, cout, no. Otherwise, now, same loop, different logic. Actually, why don't we just do this straight away? Vector, pair, hello, edges. Times n plus c. I'm converting the row and column pair into a number. R times m plus c. Yeah. So the timestamps for this are going to be wild, by the way. I'm just kind of doing some dumb things because I kind of enjoy it right now. Else if count is equal to 2, don't like that. P dot push back D. ID of a, no, it's I plus drp0, and then j plus dcp0. We're storing the directions in this vector, and then we're going in that direction so we can restore any coordinate. So this is the same for 1, except it's b. And then now we add the edge. Void edge. Okay, so now we do edge a, b1. So then ret ij is equal to, this is saying if it's 0, set it to 0, if it's 2, set it to 5, if it's 4, set it to 10. Otherwise, we will set it later. So even if it's wrong right now because it's odd, we can deal with it later. Actually, no, this is actually perfect. Yeah. So we add a similar edge between two things that are in the same column. So edge ID. So row below, j ID I plus 1. We're adding an edge between the vertical ones and telling them to be the same. We do the same thing for things that are on the same columns. So ID I j minus 1, ID I j plus 1, and we tell them to be the same. Then we also add an edge between two different ones. So for example, I minus 1 j and ID I j minus 1, telling them to be different because they're on like, they're like these two. These two have to be different. But these have to be the same, and these have to be the same. Now we do two coloring. How do we do that? Let's copy this. Bool vis range 75. Alright, void DFS. So otherwise, color of V is equal to C. Now, for each edge, for two coloring, we can do greedy. So if vis x dot first, I'm feeling we shouldn't get to this, but in case we do, like it should always be possible, but in case it isn't, then I'm not sure. I'm getting the feeling that it should always be possible, so this shouldn't be necessary, and I might add an assert later if it's wrong. But for now, I just want to test it. So if it's visited, if col v XOR call x dot f is equal to c. No, is equal to x dot second. So basically, if they're different, it should be 1. If they're the same, it should be 0. And XOR will tell us exactly that. Is not equal to x dot s, return 0. So then we have a problem. Otherwise, DFS x dot f, color v XOR x dot s. If it's 1, we should change it. If it's 0, it should be the same. Yeah, so now, I'll do the same thing. Like, this could be in the same loop, but I don't care. So ret ij is equal to 1 plus 3 times color b. This is like a hacky trick. If it's the color is 1, then it'll be 4. There's a decent chance this won't work on samples, which is fine. Again, if it doesn't work, I'll just resort to doing E, I guess. And J. Come on, why would you use different commands? Command is like the control for everything, except for actually using the terminal. Then you have to actually click the control key. So like they get you used to using the key, and then they just screw you over in the terminal because that's how Macs work. That's awesome. I love that. Doesn't even. Oh wait. I gotta do some clearing. No wait, there's no multitest. That's why. I closed the goddamn. Control Q used to be the comment, and now it means quit. So whenever I try and do that, it just closes the app because awesomeness. I better have saved. So what I actually want to do is comment this out. And control / doesn't actually work on Notepad++ because wonders. Like, there's nothing is ever going to cooperate, basically. Why is that a no? Is this a 5 no or a no? Okay. Oh, that's why. Return. Otherwise, by default, it returns nothing, and that means it could, like, die. So 1 1 1 1 1. Let's see how that works. 4 5 5 5 4. Sure, seems legit. This should be an automatic no. This should just work. Do you have to print yes? That is something I should do. And the last one is the real test case. So it does do that. Seems like it does things fine. I don't really know yet. The hard part is handling like a multiple of these. Let's look over the code. Okay, so if it's X, look at the adjacent cells, go for the plus, or count the dots. If it's odd, it's impossible. If it's even, then what the hell? If there are 2 of them, we add an edge saying they must be different because they must. If there are 4 of them, we use our protocol. And we shall see. I am again not exactly sure if this works. It could be wrong. I have sort of a feeling that it's like maybe right. Give it a hopefully, I guess. This all seems right. Remaining part is in DFS. This should be R times M. Yeah. Row times the number of things in each row. And then this is DFS. If it's visited, it's fine. for each edge if it's like that. If the coloring is not work, then return 0. Otherwise, seems fine. It's at least what I want it to be, which may not be correct, but it's at least what I want it to be. Nice. All right, so now I have a very stupid rank. This is incredibly stupid. Look at this. Yeah. So I really don't want to do any of the other problems. I think this was the only interesting one, at least. Although I do like their convenience thing. It was very nice that they made it so things weren't on the edge, because otherwise that would be like, edge case, haha, right? And it's just kind of annoying to deal with that. But in this case, it isn't. Yeah, my score is very stupid. But that's fine. I only need to solve one more problem, and then I'll be ahead of most people who have A to D. So I guess I can do E. Like, I just kind of don't want to figure this out at all. Well, I could try a bit more, I guess. And I'll elaborate on this idea more later. But for now, I'll just leave it as is. Again, it's a guess. It could actually fail system test. Like, it is based on an assumption that I don't know if it's true. But it seems to pass so far. Hopefully they have good tests. In fact, they could very easily make multi-tests by embedding separate independent grids into one big grid. And then each of those grids are independent, so each of those grids would independently test a certain, configuration. So that is something they can do, because they didn't have multi-tests originally, which, I don't know, I don't think it matters that much. Anyway, I hope this isn't digit DP. I would not like it to be, but it seems kind of annoying. So, but I want to get this as the thumbnail. I will have A, B, and F solved, and that will be it. Or actually, maybe I'll have this as the thumbnail, because this is absurd. And yeah. Let's call it strategy. I got a lot of points from F. That is definitely why it's worth it. So add 9 and 6. Yeah. Number of numbers. So basically, you take the two numbers. Well, the carrying sort of carries over. Okay, that's actually important. The odd and even digit locations are independent, because an odd will only add a carry to an odd, and an even will only add a carry to an even. So now what? Well, maybe there's a better way to do it than that. Well, I hope it's not digit DP. That would be very unfortunate if it was. I'm guessing there's some better way. Yeah, I should probably solve these, actually. These are the solutions I have to explain. I'm not going to be able to code E in time, so that's sort of a lost cause, but... yeah. I mean, okay. So... Well, again, okay, we're thinking about odd and even being different, right? So, there are in fact not that many ways to sum numbers like that. Well, wait. So, like, within the odd digits for adding two numbers normally. And within the even digits for adding two numbers normally. So really, oh, okay. So really we have two independent problems? Yeah. Okay, I guess that makes sense. Sure, we have two independent problems. Um, the number of ways to get two digits to sum to that. Okay. Right, so we're gonna add up we're gonna take the odd digits, we're gonna take the even digits, we're gonna multiply them together. Because it's two independent problems. Okay. So, Cn2n. I'll read it as a string actually. Okay, so for car CS. Actually, let's do better. So we're converting it to a number. If I mod 2 is equal to 0, odd is equal to 10 times odd plus v. So that we're appending a digit onto the end, which means we need to shift the rest of the digits by that. Alright, this should work. Kind of, actually, wait. How multitests? Actually, it's not perfect. I'm not gonna close the app again, at least for now. I don't think this works, actually. Oh, what's with that? Oh, wait, maybe I'm counting them wrong. What's happening? Why would you be 1? Oh, that's why you'd be 1. Oh, that's because I should not be reversing it. Yeah, there we go. 9, 4, 7, 44, 99. That should work. The reason we're subtracting 2 is because we are also counting the ordered pairs 0n. What the hell just happened? 0n and n0, which we don't want to do. You see the lag? Like I'm doing a full circle with my mouse and it's picking up none of it. But we don't want to count those because A and B both have to be positive, so they can only count the ones where both of them are greater than 0. That's why we're subtracting 2 from that. But essentially, odd and even are independent. In the solution, I will describe more of this idea. Okay. How's my standings now? Nice. Looks like Monogon had the same idea. Awesome. Andy's trying E, which is... I feel sorry for him. I'm very sorry that he tried to do that. That looks very annoying. Now I can do D, I guess. So you have n positive integers in base 10, and they're in base 11. So again, you want to assign as much as possible to the later digits. Does it work to just print like the number and then the rest of them are ones? I'm not exactly sure. That would work for this. It would work for the last sample. Um, if we had 1113. No, it doesn't always work to do that. If we had 1113, the best thing to do is to have 110 and 1. That would be the best thing to do. Okay, so the best thing to do is to distribute the digits. So what I mean is like, say we have like 2, 3, 4. And the best thing to do is to write 100, pretend that's 100, then another 100, then 3 tens, then 4 ones. Because then we get as many of the higher digits as possible. The problem is sometimes we can't. For example, what if we needed 10 numbers? Then what we just need to do is we need to give away ones to do as little damage as possible to the highest digits until we can split the digits. So okay, so what I'm going to do is first, this is the sum of digits, while this gives you the sum of digits. Now we're going to try to do this quickly. So Cn to n and k. While sum d n is greater than less than k. Wait, is it? Okay, n cannot be greater than, or k cannot be greater than n. 1 minus n. So if k is greater than 0, let's see. We need the highest digit of n. So r equals 1, while r times 10 is less than or equal to n, r times equals 10. So wait, this should be while k is greater than 1. If k is greater than is equal to 1, C out n. I can explain this logic later too. I kind of want to try and full solve, so that means solving E. So 97 2, 1087, sure. 17 1, 17, obviously. 111 4. Why is that a lot of numbers? Because I didn't minus k here. That is why. Did not mean to open OBS. Did not mean to open messages. I love this computer. 109. And we can't really do better than that, yeah. So 1090. Either way, that works. Same thing. Yeah. I believe it works. So again, the main idea is to maximize the number of higher digits. We do that by trying to like apportion the digits as much as we can. And if not, then we use ones because that would like get as rid of as little as possible until we're able to like partition the digits well. I could have messed up the code actually. Oh, what's with that? Why is that wrong? Test case 4, 199. Why did they not show the... Oh, that is true. Okay, wait. Maybe I'm wrong. Perhaps it is better to not do it like that. Um, how's this work? Alright. So actually, it seems like ones is like the worst thing you can do. So that was a mistake. But then what can we do? So we want like as many of the larger digits as possible, again, because larger digits are more valuable in base 11 than base 10. Oh. It's like a different kind of process. We get rid of the biggest digit until it would make us smaller than n, or smaller than s, until we run out of digits. And then maybe it's greedy. Like we use the smallest digit that will not make us run out of digits, or we use the largest digit that will not make us run out of digits. Okay, so all of this is wrong. Awesome. Actually, I can keep around this code. So while k is 1, this is 10 to the 10th, much bigger than we'll ever need. So while n minus r is less than k, r divided by 10. Try that out. So same deal, except we proportion the bigger ones differently. So we're using as high digits as possible while still making it so we have like enough. So while n minus r being less than k means that like if it's true, then we'll not have enough ones to go around. I don't know, this could still be wrong. Nice. Okay, so how do I actually do this? If it's K-circ, I don't like this problem. Actually, I don't like it anyway. But it is a problem that is required to do. So why is that wrong? Or when is it wrong? There's enough zeros, right? We have this many, then this many, then this many. Yeah. 10 to the 10th. Okay. We also kind of want to prioritize like the digits we already have. Okay, so first we'll go through the digits we already have, I guess. Stop. I'm surprised I haven't accidentally clicked that button more. Okay, I'm adding this line. It's checking if it contains at least one of this digit. So modding it by this digit times 10 means that we're getting rid of all the digits above. Then if it doesn't have this digit, it will be less than this digit, and otherwise it will have it. R is greater than 0. We do the same thing. Okay, so first we're prioritizing using the digits that we have, so that we don't like do something dumb, I guess. There's a decent chance this works. Again, I don't care about penalty, so it's fine to spam submit. Actually, failing system tests would be unfortunate, but okay, same error. Question is why? So we're using the digits that we have now. Is there ever a time where we don't want to do that? Okay, maybe we do have enough digits initially. Then that's ideal. Maybe think of it like we want as many of the biggest digits as possible. While we can do that, we continue doing that. Then the only time when we can't do that is when we run out of digits. Well, okay, so the final state might still be one where the sum of digits is large enough. Sum of digits is large enough, then what? Now I'm kind of confused. When does this greedy not work? We're using as many of the largest digit as possible. Then we're using as many of the next largest as possible. Why is this? What is this wrong? Could we want to use multiple digits at once? It is always better to merge 10 of the smaller ones into the bigger one. So maybe we think about it like we lay out all the ones. We convert S to a ton of ones and we lay them all out. Then what do we do like after? Maybe we merge some of them into bigger ones. But the issue is maybe we'll run out of like when would we not be able to use that digit anymore? Like we only run out of the biggest digit when we don't have enough value in the smaller numbers. And then we have to move on to a smaller digit. So I feel like the fix I tried to make to my greedy doesn't actually work. So what can I be missing? Well, we are. Take as many of the big ones as possible. But would it ever be better to like immediately split a big one into a bunch of smaller ones? We split a big one into a bunch of smaller ones. Um, and then what? And if we don't do that, sure. So what happens if we take this big one and then we split it into 10 tens? Is that ever better to do? I guess that would be when my strategy fails, if that's better to do at some point. But when would that be better to do? Like we're going to, would it be better? One hundred. I can't process this. Why can't I process this? Why is it so hard to process? Like I'm just trying to see if this is possible. So sometimes it's necessary to do that. Sometimes we can't do the 100 because we run out of the other numbers. Hmm. 'N is also almost 100. It's an important thing to note. 100's small. Not just for the constraints, but the fact that it could have this something to do with the answer. That certain strategies will not work because we have almost 100 numbers. $99 is less than 100. That's a thing. If we have 9... Wait, okay. So we could have 9 tens which is 990. Or 99. What? Yeah, 9 tens, which is worth 99. I really don't understand what's wrong with this. So I got rid of the quick fix that didn't actually do anything. This was the original submission. M minus R is less than K. I'm tired of this problem. Well, M minus R is less than K. Then we decrease R. There's no reason we would ever run out of R. Wait. This should be K minus 1. That's a mistake. Yeah, because we're not looking for K, we're looking for whether we have enough numbers to make the remaining amount. And we're decreasing K this iteration. Damn it. Alright. Well, okay. So, yeah, that was dumb. That was very dumb. I could try E, but I doubt I'll have the time to actually do it. Actually ended up worse than people who did A, B, C, D, E. That's kind of sad. I'm like, no, there's no way it'll work in time. How much score would I have if I did E right now? It'd be 1323, so 6600, which is very stupid. Would be very dumb penalty. Dumb penalty is like my name nowadays. Yeah, I don't know. I mean, I know how to solve it. Like, you use a segment tree, you're going to store some information in it, you're going to be able to merge stuff. I just don't want to do it, because 16 minutes is not going to work. There's going to be a crap ton of debugging, it's just going to be a pain. I don't think I'm going to do it. I don't think I'm going to be able to do it, and then I'll just have wasted the 16 minutes. And I might as well just, go for explaining the solutions. Zoom out. That's not out. So I can erase some stuff. I really don't like that you don't have full zoom here. That is very annoying. I'm definitely going to get a different drawing app after this. And it lags like crazy. Assuming it's recalculating it every frame or something, which is a pain. I don't know why it just doesn't do the selection like... like, the fact that it's lagging means that it seems like it's redoing the selecting every single frame. Instead of just having the window there, and then when I actually want the selection, I can evaluate the window like later. but that's not what's happening. So that sucks. Anyway, yeah. So there is like the potential to get a pretty good place. Maybe like top 20 or something, and then by solving E. But I do not want to do that, so I will not do that. And yeah, I will just leave this as is. E is not worth it. Or coding E is not worth it. So instead, let's do solutions right now. Alright, problem A. We have a grid, a 2-row n column grid, and we're gonna put some dominoes on it. We're gonna put some dominoes specifically so that every cell of the grid is covered. But of course, there can't be multiple dominoes on a cell. So for example, maybe we could do something like this. Right? Doesn't have to be like that, but that's what would happen. So the way we would notate this in terms of the problem is we would say this is the left side, this is the right side of the domino. And this is the upper side, and this is the lower side, or the down of the domino. This is how we would notate this. We would do this for all the dominoes. So what you're given is you're given one of the rows. You're either given the top row or the bottom row. You don't know which. But what you want to do is you want to figure out what the other row is. So for example, this row, what color did I use? Aqua. This row will be notated like this. I really need a better drawer. It lags so much. This would be notated like this. So this would be the input. LRUU, LRUU. And then we want to figure out the other way to tile it. Like the way to tile the rest of them. So the thing is, with L and R, we know that there's going to be nothing here. Because we know that there's not going to be anything in the bottom row. So for the other row, we might as well make the opposing domino also an LR domino. So that we sort of get this square going on. And so we can, in the other row, every L can be also an L and every R can be also an L. So if we have an up, then we know that it has to correspond with a down because it's a vertical domino. The other row has to have the other side of the vertical domino. So if we have an up, it corresponds to a down. If we have a down, it corresponds to an up. And so this works because every up and down is matched together, and then we're left with only the places that are LR. And because an LR works in the row we're given, we know that it will also work in the row that we're not given because these rows are already equivalent in terms of up and down. So the only things we don't know about yet are the places where there are horizontal dominoes, and it would work to just do the exact same strategy. In fact, it's the only strategy, but that's kind of more annoying to show, so I won't. I would just say, in terms of code, we're going to do that. So we're going to read in the string, and for each character in the string, if it's U, then it has to be a D in the other row, and if it's D, then it has to be a U in the other row. And I don't do anything about L and R, I just keep them the exact same. Yeah. So that is how that would work. Sorry, I'm going to be very confused a lot of ways. Hopefully it's recording. Hopefully I picked up sound well. That would be a pain if it didn't, because this was kind of an interesting round. God, how many times? I've opened messages so many times I'm trying to get back to Chrome. Well, there is Alt-Tab, actually. I should probably use Alt-Tab more. The reason I'm sort of accustomed against Alt-Tab right now is because when you have multiple Chrome windows open, it doesn't distinguish them. So you have to manually click it and do that. Which is, I mean, fine, it's just like, the hotkey doesn't work. So I've sort of grown accustomed to not using Alt-Tab because it doesn't work all the time, but then I have to click around, and then usually I miss because my mouse movements are not precise. And it's just sort of like, it's just a time. It is a time. Anyway, this problem. You get an array, you know that the mex of the array is A, and the XOR of all values is B. So the mex is essentially, you start from 0, and then you go up until you find a value that's not in the array. So the array like 0, 1, 3, it has 0, it has 1, it doesn't have 2, so 2 is the mex. It stands for minimum excluded, which kind of makes sense. It's like the smallest number that isn't there, basically. So they do have Wikipedia links. They do not have Wikipedia links. They have it for XOR, but not MEX. Okay. Sure. Why not? I guess it doesn't matter for MEX. I mean, you can define it there. Okay, so because the MEX is A, it means we have to have all the numbers from 0 to A minus 1. That is sort of necessary. Because otherwise, well, the MEX can't be that. So let's assume we have all these numbers. Assume it will let me draw without lagging my computer to death, which is not a guarantee. Oh my god. Okay, so 0, 1, 2, dot, 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 A minus 1. Right, so these numbers are in the array. That is guaranteed. We have to do that. Oh, and the problem asks for the smallest length of the array of an array that satisfies these conditions. So we know these are in the array already, right? So we might as well consider how they affect the XOR. And the constraints are not enough to manually take the XOR of 0 to all the numbers. There are many ways you can get around this. For example, you can pre-compute. You can pre-compute the XOR for all numbers from 0 to 0. And then, okay, I'm just going to talk it out because I can't draw it. You can do 0 to 0, then 0 to 1, then 0 to 2, and etc. in sequence, like pre-computed before you handle any test case. And that would work because like the XOR from 0 to 3 is the XOR from 0 to 2, but including 3. So you already know the XOR from 0 to 2, so you can take that value, XOR it with 3, and that's how you get the XOR from 0 to 3. Now, if you did this, you would be able to notice that there are certain patterns. There are certain patterns that it's sort of like cyclic in groups of 4. Now, I will try to draw out the numbers 0 to 7. I will probably fail. I feel like I should tone down the image size, but I'm already too far in, so I'll do that for the next one. So the key point here is that the XOR of these 4 numbers is 0, and the XOR of these 4 numbers is 0, and the XOR of 8 to 11 is 0, and so on, and so on, and so on, which means that every 4 numbers we end up back at 0. And the reasoning is because, well, this is 0, because, like, just try it, it is. And then this is 4 XOR 0. This is 5 XOR 1. This is 6 XOR 2. No, sorry. This is 4 XOR 0. This is 4 XOR 1. This is 4 XOR 2. This is 4 XOR 3. So we get this relationship where we XOR everything by 4. So XOR is its own inverse, which means that if you XOR, like, A XOR A is equal to 0. And XORing a number with itself will cancel itself out. So that's nice because we have an even number of 4s here, which means that all of these 4s will cancel each other out. So really, we're just XORing 0, 1, 2, and 3 again, and we know that's 0. For 8, it's going to be XOR 8. For higher numbers, it's going to be like XOR 12, XOR 16, etc. But it will always cancel itself out. Yeah, try not to do that. So now we just need to figure out what the pattern is. So every 4 numbers, we're gonna observe similar behavior. We just need to figure out what that behavior is. So we can do it for one case, and then we can figure it out. So we know this is 0 automatically. So here we end up with 4. Now here we end up with 4 XOR 5, which you can evaluate as 1. It's always going to be 1. You can check it with this one too. In fact, it's probably easier to just check it with this, but this sort of makes it more general. So now we get 1 XOR 6, which is 7, because 6 is even, so it doesn't have a 1 bit, so this would add the 1 bit. And then, of course, 7 XOR 7 is 0. All the bits cancel each other out. So representing this pattern, if we have n, and we want to ask what the XOR of numbers from 0 to n are, then the answer here is going to be, here it's going to be n. We're just going to return n. Here it's going to be 1. Here it's going to be n plus 1 because we get that extra 1 from right before. And here it's 0. So based on what n mod 4 is, we can figure out exactly what our XOR is going to be. So now that we know this XOR, what do we do with it? Well, if the XOR is exactly b, so let x be like the XOR that we're interested in, the XOR of numbers from whatever to whatever. I'll use grape. I like grapes. So if x is equal to b, then we don't need to add any more elements, of course, because the XOR is already what we want. Now, normally we would be able to add some other number, like a single other number, and it would work. But the problem is, what if the number we need is a? And the problem with that is we can't have a because the mex needs to be a. And so by definition, x cannot be in the array. So if x is equal to a XOR b, and therefore the only way to make the XOR equal to b would be to stick on an a, then we need to add on 2 extra numbers. I need to draw so slowly here. I'm sorry for this. Should have planned this out better beforehand. No. You see how slow? You see how slowly it's doing those undo operations? Oh god, what have I done? Okay, so if it's that, we need 2 operations. And otherwise, then that number is not a, which means it's something we can put in the array. So whatever x, so we're going to add in x XOR b to the array otherwise. So if this happens to be a XOR b, then x XOR b XOR x. Wait, hang on. So if x is a XOR b, then x XOR b will be a XOR b XOR b, which will be a. And otherwise, it will be exactly what we need. Because we have x currently, and we need it to be b, so the x's will cancel out, and we'll end up with b. But if x XOR b is equal to a, then it doesn't work. So that will be what we do here. Now, the final question is, can we always do this in 2 operations? And the answer is yes. We can add on, for example, we need to get rid of the a. So what we can do is we can add on a XOR like 2 to the 50th or something. Some number that's so big that it can't possibly interfere with the max. And then we can also add on 2 to the 50th as well, so that the only number, so that the total XOR of these 2 numbers is a. And therefore, that's exactly what we want. We want to get rid of the a, and we want to be left with b here. So this is the final casework. So initially, we have a elements in the array, because that's how many we need to get the mex in the first place. Then to make the XOR work out, we have some extra numbers we need to add depending on casework. So this is how I find the XOR. Again, you can pre-compute, but I decided not to do that. So now if x is equal to b exactly, then we do nothing. We also start off the answer to be a. And then because we're interested in the XOR numbers from 0 to a minus 1, because we do not have a. So we need to consider a minus 1 in this case, in what we're doing here. So I subtract 1 from a, and then I add 1 to a to make it back to the original a. So now if x is equal to a XOR b, we need 2 numbers, otherwise we only need 1. Then we can print the answer. Yeah, I think that's it. Ultimately, casework. Okay, I'm going to scale down the image size by a crap ton. Let's do like 40%. See if that works. Hopefully it should be less laggy. Okay, so just don't use such a big image because they have a really big problem with that, I guess. Alright, now it's done. So, carrying conundrum. Basically, we're adding numbers together, except it's like sort of wrong. Instead of carrying a number to the next digit, we're carrying it to like a digit after the next digit. So for example, like 3 plus 7, hang on, like 003 plus 007. When we add them together, normally we would have the 0 and we would carry the 1 over here, then we get the 1. But in this case, we missed. We went too far here, so the 1 is actually here. So we end up with 100. So 3 plus 7 is in fact 100 based on this twisted version of math. So the question is, we're given a number n. We're interested in how many pairs of positive numbers, like a, b, work so that a plus b is equal to n. And they have to be positive. So a is greater than 0 and b is greater than 0. Yeah. So sorry, I'm blanking. This is what we need to do. So the question is, and remember this is the special plus with like the weird carrying. So how do we do this? The main step to observe is that things are sort of independent. In the sense that, consider this. So this digit will give a carry to this one. Then this digit will maybe give a carry to 2 digits ahead of it. Then that one will give a carry to 2 digits ahead of it as well. And what we're doing is we're skipping all the digits in between. So these digits, specifically at odd positions, will never affect the ones at even positions. And even will do the same thing. We get a digit here, it will maybe affect this one, and it will maybe affect this one, and it will maybe affect the 1, 2 ahead of it, and so on. But the even will never touch the odd, and the odd will never touch the even. Which means that the even and the odd are separate. Okay, so now it helps to solve an easier problem. The positive thing is kind of annoying. Because what if A and B, what if both even and odd are 0? Then it kind of doesn't work. Yeah, so in the case, so let's first just solve the problem where they can both be like non-negative. So A and B, A could be 0 or B could be 0. Now basically, we have some odd digits we need to satisfy. For example, say n is equal to 2354. We need the odd digits to make the number 34, and we need the even digits to make the number 25. These are independent of each other, which means also, like, note that, like, for the odd digits, if we consider only the odd digits, it's basically like normal addition, because the carry throughout the odd digits will only go one position further in the odd digits. So really, within the odd and the even worlds, we're adding normally. So really we're asking, how many numbers are there from, how many A, like non-negative A and non-negative B, sum to 34? And how many sum to 25? Then we multiply those together. And, well, the answer is we can have any number from 0 to 34, and then 34 minus that number. So this is A and this is B. And the numbers between 0 and 34 are that plus 1, so really we have 35 numbers. No other like configuration will work. This is what we can do. So we have 35 numbers. So in total, the answer for this will be 35 times 26. The problem is, again, that now we're dealing with non-negative numbers, but we can't have zeros in this case. And the way to handle this is that there are only actually two possibilities for when we have zeros. Either we have 0n or we have n0. Because n is not 0, these cases are distinct. So really all we need to do is subtract 2 at the end. So we find out the answer for allowing zeros, and then we subtract 2 for the cases where there are zeros. And yeah, that works. So we extract all the odd digits and we extract all the even digits, and then we make these numbers. Call them x and y. Then the answer is x plus 1 times y plus 1 minus 2. Minus 2 again because of the special cases. So let's look at the code for that really quick. We're going to look at each of the digits. Now, if it's at an odd position, it doesn't actually matter which is odd and which is even. It just matters that we don't mix them up. So if it's at an odd position, then essentially we're adding a digit onto the end. So the rest of the digits have to be shifted backwards. And by that, we multiply them by 10 to move them up in the decimal. So it's odd becomes 10 times odd. It's 10 times whatever the old one is plus the new digit. So what I'm saying is, say we have 32 and then we make it 325. So really it becomes 320 plus the new digit 5. So that's why we multiply by 10 and then we use that formula. So the same thing for even. And yeah, then formula. Done. Okay. I'm glad it doesn't lag as much, but I don't know. Maybe it's fine. I don't like that we have to edit screenshots, but I guess I can just make that work. Or I'll try and find some better one later. Yeah, okay. Next one. You want a list of integers with a specific sum in base 10 and the maximum possible sum when considered in base 11. So what I mean is, say you have 97. You need two integers that sum to 97 normally. And of these, you want to pick the two integers that, if you think of these as base 11 numbers, what's the highest sum you can get? So cases where this matters, for example, say we have 11. Then we can write it as 9 plus 2. In base 11, it would be 10, or 1, 0. But if we write it as 1, 0, 10 plus 1, in decimal it sums to that. But here, it still works. It sums to 11. So here we get, in base 11, we get this. These are in base 10. All of these are in base 10. This subscript is sort of a notation saying what the base is, which is equal to 11 in decimal, and this is equal to 12 in decimal. So it does matter the way you do this. Essentially, you want to take as many of the higher digits as possible. And in fact, that is all it is. You want to take as many of the higher digits as possible. This was dumb. Don't mind this. I was sort of just messing. I had a small mistake and that screwed me up. A lot, in fact. But really, that's all it is. We want to take as many of the higher digits as possible. So suppose we have n equals 1194. Or not n. The sum, I sort of mixed it up in my code just because I like to think of it that way. But sum is 1194, and the number of numbers we need to take is 7 or something. I don't know. So first, we're trying to take the highest digit possible. Actually, wait, this is not a great example. Let's do 1124. Something like that. So first we want to take the highest digit possible. So we can't take 10,000. That would put us in the negatives. But maybe we could take 1,000. So the criteria for being able to take a digit is, if we take this digit, is the rest of it enough? Will we still have enough for 6 numbers once we take this digit? So in this case, we do. 124 is at least 6. Note that what we can do is, if we have s is equal to n, we can have that many 1s and then it would still work. So really, the only time it doesn't work is if n is too large. Specifically, if the remaining sum we have is less than n. So here, we take this, now we're left with 124. And n equals 6. So can we take 100? We can. I'm going to make this 21. Because otherwise, actually, it actually exactly works out. So that was a dumb example. But we take 100. Now we're left with 21. So n is 5. So on. We take two tens. Then n equals 3. And we're left with... no, sorry. We take 1 10. Then we're left with 11. Then n equals 4. Now we cannot take another 10. Because that would leave us with not enough numbers. So instead we go down to the next digit and we say we'll take a 1 instead. And then we're left with 10 and we have 3. Once again, we cannot take a 10 because that would leave us with not enough numbers. So we take a 1, we're left with 2, etc. And then for the final number, we're left with 8. And for the final number, we just like print the whole number. There's nothing else we can do. So really, it's just greedy on the highest digit you can take that makes it so you have enough numbers left over. So code-wise, my subtle, I don't know if it's actually subtle, it's an important bug that I put k here instead of k minus 1. And that means that it's asking, will you have enough numbers left after you take this one? But what I was asking was, will you have enough numbers left like before you take this one, even though you've already taken this one? It's like it has to be k minus 1 because when you take this number, that's the new number of numbers you need. If you have k, then you're sort of making it harder on yourself. You're saying you need another number when you really don't. So we start with like a huge number, 10 to the 10th. And then while we don't have enough space to take that number, we make it smaller and smaller until eventually we find something that works. We print that number, update our values, and then when we have exactly one number left, we print that number exactly. And the greedy works sort of because we always want the higher digits first. We want as many of the higher digits as possible because the higher digits are more valuable in base 11 than the lower digits are. So really, we want as many high digits as possible, and this greedy just happens to be the best way to do it. Because we're only not taking a high digit if it's not possible to do so. That is how that works. Yeah. Wow, that's a lot of system tests. Yeah, we're only not taking a digit if it's not possible. Okay, this one sucks. Like it sucks. I'm going to look at the submissions for E. I'm pretty sure a lot of them are going to be not nice in the time limit. So 561, 390, 451. Let's try accepted. Yep, 530, 1981. It's a segment tree problem, as far as I know. I mean, maybe there's a better solution, but I don't know. So basically, you have an array. You can change an element as a query. You have an array, you have a bunch of queries on it. One query is change an element. The other is asking how many non-decreasing subarrays exist in the array. So what I mean is like, so we have like, not in the array, in a specific subarray. So like, how many subarrays are there? So say we have like 2, 1, 4, 3, for example. Then I query this subarray. Now this is non-decreasing, this is non-decreasing, this is non-decreasing, and this is non-decreasing. So the answer here is 4. Non-decreasing is like sorted. So I query this, then we just have this and this. If I query this, then we have this, this, and this. I think you get the idea. So, and we can change elements. So I can make this 2. And I get 2, 1, 2, 3. Now I query this. Of course, the change applies. So now all of these work. So the answer here is now 6 instead of 4. Right? Like you know what updating is. So the way to do this is we're going to consider the adjacent gaps between the elements. So we're going to create a new array that represents the adjacent elements. We're going to say if AI is less than or equal to AI plus 1, then this value is 1. Otherwise, it's 0. So in this case, 2 is not less than 1. which means that this would be 0. 1 is less than 4, or less than or equal to 4, this would be 1, then this would be 0. Right. Now, why does this array help? Well, it's basically saying this using this array can tell us how many subarrays there are of length more than 1. So let's say, like, for example, we query these 3 numbers. Then in this case, every individual element is a subarray on its own. But then the other amount of subarrays we have is like each group of ones, like every one represents a pair of adjacent elements we can take as a subarray. So let's take a better example. Let's take like 1, 2, 4, 3. Then the array here would be 1, 1, 0. So if we query this whole thing, I'm using random colors now. Essentially, because these are all ones, we know this would work, and this would work. Yeah, so we know that these elements would work. Also, again, note that we're strictly considering elements that are actually, I feel like maybe this adjacent thing doesn't really matter. Well, wait. I'm trying to think of like the best way to handle it. I believe there is not a best way to handle it. Well, I mean, sure. Yeah, we'll use this. Then this represents a group of 3 elements, and any subarray of this is going to work. I mean, yeah, sure, I guess. All right, so now we're gonna build a segment tree on this. So now when we update an element, it'll change. It'll like say we change this to 1, then this will flip, and then we update the array. So now we need to like keep track of it with a segment tree. So the way we like merge elements, well, we're considering like 2 nodes in the segment tree that we want to merge. So what do we need to really store? Well, first we need the answer. We need the number of subarrays, specifically of length greater than 1, within this node. Then we also need some other information. Specifically, what we need is, what we want to find out from the merge is how many subarrays are partly in this node and partly in this node. So what we need is, let's say, for example, we have some array like this, 0, 1, 1, and then like 1, 0, 1, right? So the number of subarrays that work are the number of subarrays that, well, wait. It might be better to build a segment tree in the elements. Yeah, I think I might be actually. Let's scrap this array of 0s and 1s. I don't think it helps. Basically, we're just gonna build the segment tree over the elements. So within the segment tree, let's say, for example, we're going to merge a segment tree representing the elements 1, 2, a bar here, 4, and 3. So how many do we have between them? Well, If this is not less than or equal to this, then automatically we have 0. Because like there's nothing we can do. Otherwise, what we're interested in is how many elements can we pick from here and pick from here so that it will still work. And the information we need for that is, well, what's the longest subarray, like longest sorted subarray starting from here? And what's the longest sorted subarray going from here? In this case, that would be this. In this case, that would be this. So then we can pick any element from this and pick any element from this, and then we can multiply those together, and that gives us the number of subarrays we can pick in total. But if we included the 3 at all, it wouldn't work because this is decreasing. So it doesn't work. So what we need is, we need the number of valid choices from the right for this node, and we need the number of valid choices from the left of this node. And we need that for every node. We need the number of valid choices from the left and from the right. So we need like choices for left and right. And it represents like from the right, what is the longest sorted subarray with that's like attached to the right. So how many elements are sorted on the right and how many elements are sorted on the left? Is that seriously how long its history is? Okay. So we store the number of sorted on the left and the right. And then in merging, well, we add the two answers together, of course. Then we figure out how many new things we have between them, and then that also contributes to the answer. And then to maintain the number of sorted on the left and the right, if the entire array is sorted, then this whole node will be whatever's on here, plus however many there are sorted on this. Otherwise, if this whole thing isn't sorted, then it will just be the number of sorted on the left. So you have to consider, like, maybe sometimes it bridges between and it uses like both of the nodes. And sometimes it doesn't. And you do the same thing for the right. If the whole right is sorted, then you depend upon the value that's here, because this would still be sorted. And if the whole right is not sorted, then you depend only on that. And then you merge nodes and then answer, segment tree, you know, stuff. You can maintain this information. It's O of 1 to merge. Maybe it's not actually that bad, but I don't think I would have been able to write it in 15 minutes, so I did not try. But that would be how this works. This is the information you need to store. Have fun trying to merge it. I will code this later. After I finish recording, I will like write up the solution to this, but not right now. Like after I'm done. Let's see how this goes. How have my submissions done? I passed A. That's a lot of system tests. So I guess all of like a lot of the solutions happened on A. I guess that's where most of the action happened. Yeah, there are already 12,000 solves on things. That is very cool. Look at me in like 10,000th place. Yeah, imagine this. This is so good. Yeah. Interesting. Also tried to do A, B, C, and E. Surprised not that many people did A, B, C, and F, I guess. Well, a lot of people did end up doing F. Yeah. A lot of people like clutched out F. Interesting. Okay, so the final part is 1-4 overload. So, oh yeah, by the way, I don't have code to go over for E, sorry. But the final part is F. I will not read the statement for this. It's kind of annoying. But we're going to consider the marked cells. So let's consider a single marked cell and how many cells it has, how many unmarked cells adjacent to it that it has. So we'll say circle is marked, and then square is not, just for notation. So let's say, for example, we have a configuration like this. So this is adjacent to one marked cell. Well, how do you get a multiple of 5 when all you have is 1 or 4? You can't. So in this case, you cannot, this will not succeed. You cannot have a multiple of 5 here, so it's not possible. Suppose you have a similar configuration like this, where you have 3 unmarked cells, and then 1 marked. You can try all the possibilities. It will not work. There is no way to get a multiple of 5 with 3 unmarked cells. Like, again, feel free to try. You will not succeed because it's not possible. In particular, like, the reason is because 1 is 1 mod 5, and 4 is -1 mod 5. So an odd number of values will not sum to 0 because each of them is either 1 or -1. The only way out of it would be to have like 5 1s or 5 -1s, but you have only 3, so that doesn't work. That's why they chose 5 instead of something like 3, which I sort of get now. Yeah. So if we have any marked cell that's adjacent to 1 or 3, it is impossible. What about the other cases? If it's adjacent to none, then we just have 0, works. If it's adjacent to 2, this is where it sort of gets complicated. We need to put the 1 and the 4 so that they're opposite each other. We need to have 1 adjacent 1 and 1 adjacent 4. We cannot have 2 1s and we cannot have 2 4s because that won't work. And the other case is when we have all 4 marked cells. In this case, the only way to have it work is to have 2 1s and 2 4s. And the question is, where do we do it? So one of the issues with like sort of like blindly choosing 1s and 4s is that maybe we get a situation like this. Maybe we get something like this, where we do something like 1 and then 4 and then 4. And then this one is forced to have 2 4s next to it. And then that loses. So my thought for addressing this was to avoid this situation by instead coloring it so we get, so opposite sides are the same. So like the 1s are opposite each other via like rows or columns, and the 4s are also opposite each other. That way in this situation, we're guaranteed to have a 5 no matter what. It's always going to work if we have something like that. Assuming this is true makes the problem doable. If it were not true, I would have no idea what to do with my life. But assuming this is true makes my solution work. So I don't have a proof for this assumption. The only reason I thought about this is because it would resolve this situation. It would resolve that issue of impossibility. But I'm fairly sure that sort of like intuitively, if you do this and you don't have this situation where you have 1 or 3, it will always work out. There will always be a solution that works for it. I do not have a proof for that, so I'm sorry about that. I usually do try to prove things, but I have no idea what to do with this. So, as it turns out, that passes pre-tests. I'm not sure about system tests because that's still going, but that's what's going on right now. So I will get back to you on that. It might fail system test, in fact. That is possible, but who knows? So really what we're saying is, now we want to figure out how we actually assign the numbers. And well, we have 1s and we have 4s. There are 2 possible labels to each number. So really we're trying to color the grid in 1s and 4s such that like we have certain constraints on what can be what. For example, if we have this situation, we have the constraint that these must be different. We have like a different edge. These must be different. In this case, what do we do here? Well, we have different edges around all of these 4 places. All of these must be different from each other. And we also have, actually that's enough. I didn't even think about it like that, but that is enough to make it work. What I did was, you can make it like strictly in terms of different edges. Actually, maybe that makes the proof easier. So if you think of, so what I did was, I sort of did it like this. So this must be the same, this must be the same, and then these 2 must be different. But thinking of it in terms of only different edges might actually make the proof easier. Now you're basically arguing this graph has to be bipartite. If this graph is bipartite, then you're two coloring a bipartite graph, which is like very known, and it's always possible because you color the things on one side one color and the other side the other color, and because it's bipartite, it will work. So the only question is this graph bipartite? If it is, then this would work. So yeah, I'm sort of figuring out this proof right now, in fact. So the question is, when would this graph not be bipartite? Honestly, I don't know. I do not know. But okay, wait. I'm gonna go through an example. Suppose you have something here. Actually, maybe you could have something like this. So then this is 4. And you have something here. So this is 1. That could actually be a problem. Am I about to fail system test here? That could happen. Wait, okay. Could that actually occur? I mean, yeah, it could. What if this is right? Okay, it is right. Why is it right? That's my next question. Oh, wait, okay, yeah. Because in this case, this would not happen, because this would have to have 4 next to it, and then I would color it differently. I would make this a 1 and so forth. So let's try not doing that. So let's say all these are marked, but then we don't actually have this problem. I don't know. It boils down to a bunch of casework. I'm assuming there is eventually a way that you can prove that this graph is bipartite. I am not exactly sure how. Yeah, this scoreboard was funny. I'm not exactly sure how you would do this. But I'm assuming it is possible. Because, I mean, it passes system tests, so I hope it works. Essentially, my argument boils down to, like, every time you would come up with a reasonable counter case, it turns out, like, you would have to have this so that it's adjacent to 4 things, and then it would match my construction. And then everything would be fine. Maybe it's like every time you have something that's like, it has 2, it sort of like creates a bridge. And then maybe that bridge sort of like inverts things. Like you would have a 1 in one place and a 4 across the bridge, but then it's like isolated. I don't know what I'm saying. I'm very sure what I'm saying is not understandable. So I will just leave it as it is right now. Yeah, sorry, I don't have a good proof. But, let's open messages again. But that's my solution. I'm adding these edges, then we color the graph. And then we print 1s and 4s and whatnot. So here, first thing I do, I go for x's. Then we are counting. We're counting the number of adjacent things to each x. Then if it's odd, it's impossible. So we print no. We're done. The break doesn't actually break out of the whole loop, but it doesn't matter because no matter what, we're not going to print anything anyway. So if the count is 2, we are adding an edge between the 2 cells that it's like adjacent to. Like maybe we have something like this, and then we still have to have this edge that these 2 have to be different. Yeah. So we pick the 2 cells that it's adjacent to, the 2 unmarked ones, then we make them different. So 1 represents that they have to be different, a 0 represents that they're the same. So for count equals 4, we take the ones that are like on the same column, we say they must be the same. We take the ones on the same row, and they must be the same. And then the ones that are like the rows and the column, the row one and the column one must be different. So it's essentially adding in these three edges. And then the answer for this, like the cell number is just 5 times like the number of, like if we have 0, the answer is 0. If we have 2 adjacent, it's 5. If we have 4 adjacent, it's 10. So this formula works. And it only fills in the one with x's, so it's fine. Then now we color the graph. Graph coloring is very standard. You basically just greedy it and you check if it's possible. And I'm guessing it's always possible, but really you start with some color, then you look at all the adjacent edges and you assign them the colors that they need to be. And then you do that until you color the whole graph. Because there's only one possibility for the other color, it's like guaranteed that if it doesn't work, there's no way to do it because there was only one way to do it and that one way doesn't work. So that's why greedy sort of works for this sort of thing. So then here, if its color is 0, we set it to 1. If its color is 1, then we set it to 4. It's just like a formula. And then print. Yeah. So that's how that one works. Yeah, and then I got C fairly quickly. And there we go. Yeah, okay. So about the problems themselves, I guess I can comment on each of them. I don't know if you guys like that, maybe? So A was like, I mean, it was fine. It was just a bit of logic, working out just the problem's sort of nice. Everything sort of works out. Like you can just take the complement and it's nice. B, I don't like its positioning. I think the solve distribution, I don't know. There was a harsh drop in this solve distribution. But I don't like the trend in there being bitwise problems early on. Like for example, I saw bitwise in A, which is annoying. And it was sort of like an intuition thing, but if you're not familiar with bitwise, then it's just a pain. So it also makes it a pain to explain for me. So I don't like that either. But yeah, I don't know. What do you guys think about having like just concepts in general in the early problems? I think in sort of like the introductory problems, it's better to not, but I may be wrong. You guys might like them, so go ahead, tell me off. Oh, battery's actually draining. Next one, this was kind of cool. It looked annoying, it wasn't. Yeah, go ahead, try it if you didn't solve it. This one also looked annoying, and it was, but that was sort of more my fault than anything else. This one just is annoying. Like I'm gonna look at some other solutions, see if anyone did it without a segment tree. Nope, segment tree, and then doing some stuff with the merging. This is a very standard problem. Like there is, yeah, that's stupid. Monogon does like to get mad at problems, fairly, of course. Like I would probably use similar variable names for such a problem. But yeah, counting subarrays in a range with updates that satisfy certain properties. Very original. Very original problem. Last one. This was pretty cool. Sort of hinged on a guess. I'm sure there's a way to prove it, but it is more guessable than anything else. I don't know what to say about that. I guess it's fine. It was still a pretty cool problem overall. But yeah, this is my reward for solving F. Going behind everyone A to E because my penalty was so dumb. I guess that's all I have to say. Hopefully you enjoyed this contest. Yeah, hopefully the stuff worked for OBS. And cool. Goodbye.